Welcome to the final chapter, Chapter 10. Okay, so this is problem 10.1. There are three different possible structures known as isomers for a dibromoethane molecule. One of them has no net dipole moment, but the other two do. Draw a structure for each isomer. Include hydrogen atoms. Now, I think that these structures are kind of hard for you to know the connectivity. So I think for a molecule like this that's not necessarily straightforward what the connectivity is, on the final exam you'd be given that. So you can, carbon typically bonds to itself. So when you see C2 here, carbon is connected to itself. Hydrogen and the halogens typically form single bonds. So your choices for connectivity could be this connectivity, or you can put a hydrogen on each carbon and put a bromine on each carbon. Like I said, so now one of them has no net dipole moment, but the other two do. Draw a structure for each isomer. Well, the first thing you have to do when you're dealing with dipole moment and polarities for the molecules, you have to draw your Lewis structure. And then you're going to look at the geometry, the molecular geometry. And we'll talk about that more too, about the VSEPR theory, the molecular geometry, molecular shape and polarity. This is all section 10.5, page 438. And there's an example, 10.5, on page 441. So if you remember from last chapter, in order to draw these Lewis structures, you have to figure out the connectivity where you have the most electropositive element as your central atom. Now, the second thing you do is you total up your valence electrons. So we have 2 carbons, and carbon is in group 4. So 4 times 2 is 8. That's for carbon. We have 2 hydrogens. Hydrogens in group 1, so 1 times 2 is 2. And we have bromine, which is group 7, and there are 2, so 2 times 7 is 14. This is a neutral molecule, so we can just total these up, and we get a total count of 24 valence electrons. Now since we have the connectivity, we go ahead and put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we're going to go all the way to 24. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? Actually, let's just put it together and leave it like that. Okay. Now, you check. The next thing you do when you're drawing the Lewis structures, you check to see if you have the octet. So remember, hydrogen has a duet, which is 2 for a complete shell. And then bromine has 1, 2, 3, 4, 5, 6, 7, 8, because you count these 2. and it has a complete octet. That bromide has a complete octet. This carbon has 1, 2, 3, 4, 5, 6, 7, 8. That carbon's fine, but look at this carbon. Not happy. It only has 6. So what you need to do at that point is you need to take these lone pairs here that are adjacent, and you're going to make a double bond. So in order to get the correct Lewis structure, we're going to redraw. And this is kind of simple because everything else stays the same. So carbon, hydrogen, now we draw a double bond, bromine and bromine. And then you put in your lone pairs, which is just really on the bromine here. And then when you check to make sure everything has its complete octet, so the hydrogens have a duet, the bromine has an octet. Now look at your carbon, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is a correct Lewis structure. Now, once you do that, then you can look at the geometry. This first carbon, hopefully by now you understand that it's bonded to 3 groups, and 3 groups would be trigonal planar. And then this carbon here is also bonded to 3 groups, and it's trigonal planar. And your dipole moment, this trigonal planar, this is basically, I'm looking at table 10.1 and applying it's on page 434, section 10.1. And there's 3 bonding groups, 0 lone pairs, so this is trigonal planar. So you always have to look at your molecular geometry shape when you're trying to assess dipole. The polarity here, then whenever you have lone pairs, you're going to, it's the pool. The polarity is really the pool within that sigma bond. So you have a sigma bond here. And so I always think of them as like tug of war. And these electrons pull the electron density. You can show this by the arrow. And so this molecule is going to have electron density higher towards the bromine because they're lone pairs. Lone pairs are negatively charged. And you see this part is a positive. So we draw the positive here, and it's pushing the electrons. You see the arrow? The electrons, the electron density is going away towards the bromine. So you have to look at each bond, and that's your bonds that they're going to have the greatest impact. And then if you kind of add those vectors together overall, you would have some kind of dipole moment. And this is like this kind of funny U, and that's a dipole moment. So it's greater than 0. You're not going to know exactly what it is. You'd have to have that measured in the lab. So that would have a dipole moment of greater 1. But the question wants you to draw 2 structures, and one of them has no net dipole. So if you remember correctly, I drew this one here. If you throw in your electrons into your Lewis structure, you're going to draw a double bond similarly, and then you put your lone pairs. And so we'll just go ahead and draw that. And then if you draw your dipole moment now, you really look towards your lone pairs here, and then you have here, and that will actually cancel out as well. Okay, so that's going to be a 0. So that will cancel out, and that is your answer. This is problem 10-2. This is a problem you need to submit. Now, for credit on this problem, you must draw the molecular geometry. So you have to draw these out. You must draw these and show the molecular geometry for credit. Okay? Because Otherwise, it doesn't help you any. So, in this problem, X is your central atom. Y represents outer atoms. I call them terminal atoms, right? Or outer atoms. Z represents lone pair. So we're going to redraw these molecules like such. And while you do this, I think it would be beneficial for you to have your TRO book open to table 10.1, which is page 434. And what I'm going to do is I'm going to redraw these molecules, each one, and then I'm going to find the similar molecular compound that's in table 10.1 and then classify them. So that's what I would like for you to do. So I'll talk about each one of them. Okay, so the first one is, I'm going to give us some space here. The first one, you would have X as your central, Y are your groups, and then you have one lone pair. Now, this molecule, if you look at table 10.1, looks a lot like this molecule. And I'm not going to draw in the lone pairs on the terminal atoms, okay, because we only care about the central atom. So this you need to be applying your VSEPR. VS, valence shell, electron repulsion pair, or electron pair repulsion. Okay, so first you write your Lewis structure, and then you look at your central atom. And then you want to count the groups around that central atom. And if you have no lone pairs, then your electron geometry will equal your molecular geometry. But if you have lone pairs, then it's going to change a little bit. So when you look at this structure here, your electron geometry is set by, and I call these groups, the number of groups. I'm going to go ahead and open my book to 434. I call these electron groups. You see bonding group and lone pairs. So the electron groups, make sure a double bond is counted as a single bond when you do this. So there's 1, 2, 3 things. I sometimes say things or groups, okay, so I exchange these. So there's 3. So there's 3 groups here. And if there's 3 groups, then it's going to be, if you look at your book, trigonal planar. And you need to go ahead and memorize. Whenever I see trigonal planar, if it's just 3 groups without lone pairs, I just go ahead and associate 120 degrees. Okay, so just remember that. 120 degrees puts 3 things in a flat plane. So this is flat as a pancake, flat as a piece of paper. Now, the problem is we have a lone pair here. And this lone pair then causes a bent structure. And that's your molecular geometry. So whenever there's a lone pair, your molecular geometry likely will not equal your electron geometry. So you can look in that book. So this is going to be bent, and it's going to be less than 120 degrees. So the first one will be bent, and it's approximately or less than 120 degrees. Okay, so then we go to the second one, and the second one is, go ahead and draw X. Now we have 4 groups, so 4 groups, Oh, and this is like water. I don't know if water's on there or not. Is water on there? 4 groups? Yes, it's the last one. So if you think about water, you've probably already drawn this or seen it drawn. Water is the same as this one here. Now, there are 4 groups. So we look at the central atom, which is oxygen. You see 4 groups. 1, 2, 3, 4. 4 groups is tetrahedral. And that's 109.5 degrees with tetrahedral. So, our electron geometry is not going to equal our molecular geometry. And the reason why is because we have lone pairs. So when you have 2 lone pairs, it's going to push everything down. And now you're going to have your molecular geometry is going to be bent. And it's going to be less than 109.5 degrees. So this molecule will go here, X, Y, 2, Z2. We'll just go ahead and check these off as we go. Okay, the third one, we have X. We got how many groups? 3 plus 2. So we have 5 groups. And so this is going to be trigonal bipyramidal. So trigonal means they're already going to be in the plane, the 120-degree plane. And then you have bipyramidal, you have something on top at 90 degrees. It's called an axial. And something coming straight from the bottom, which is an axial, 90 degrees. And those are the positions. Now, when you have 2 lone pairs, because you see here, actually I'm sorry, we have 3 lone pairs. When you have 3 lone pairs, you got to look at where you put these lone pairs. And the lone pairs for this, they take up all equatorial positions. So these would actually be 120 degrees from each other. And then on the top, you would have Y on the top and Y on the bottom. And those would be 90 degrees. And this would be 90 degrees from here. The example that they give you is xenon, and they put xenon here, and they put these equatorial, and this is actually linear because we have lone pairs. So the trigonal bipyramidal is the trigonal bipyramidal. If you kind of turn it the other way without the lone pairs, it would give you a linear. So this molecule goes here, X, Y2, Z3. Okay. All right, so the next one, I'll come down here, X, Y3, Z2. And once again, we still have 5 groups. 3 plus 2 is 5 groups. So our electron geometry is still trigonal bipyramidal. Now, when you have 2 groups, you still put them equatorial. Okay, so we're always putting the electron groups equatorial. So when we redraw this, we have the Y here, and we have Y here, and this is going to take up 2 equatorial groups, and then we have the Y at the top. It's kind of, so can't really see this here. See if we can erase that. Okay. So we have this equatorial and we have Y here. The example that your book gives you is with bromine bonded to 3 fluorines. So you kind of always want to put these lone pairs in the equatorial positions. Okay, and then what does that look like? Because you have lone pair, the molecular geometry is going to be different, and these are called T-shaped because it looks like a T. You can see how that looks like a T if you turn it and rotate it. So this would be T-shaped. So X, Y, 3, Z, 2 is T-shaped. Okay, the next one is X, Y, 4, Z. So now we're looking at 5 groups, and that's the same as we have been. So our electron geometry is trigonal bipyramidal. And we're going to put our 1 lone pair equatorial. So let's go ahead and put the Y groups axial and put another Y group. These are equatorial. Then you can just draw the lone pairs here. And then when you look, the example that the book gives you is with sulfur. And sulfur is bonded to 4 fluorines, and you're given a lone pair there. And this structure, you can see it looks like that. They call this the seesaw structure because it looks like a seesaw. So this compound would be under the seesaw X, Y, 4, Z. The next compound is X, Y, 4, Z, 2. Now we are in to a group of, we got 6 groups, and this is octahedral for the electron geometry. And so the central atom is going to be there, and then 4 groups actually go on the planar side. So where we've been doing the equatorial, now we're going to put 4 groups, and then we have 1 axial on top and 1 axial on bottom. So now the interesting thing here is when you add a lone pair, the lone pair here, when you add lone pair, they go axial. Now before, with the trigonal bipyramidal, the lone pairs, when you add in, were in the equatorial position. So here we're going to have 2 lone pairs, and they're going to be in the axial position. And now we have the 4 Y groups, and they are actually going to go and form a square. And it's called a square with 2 lone pairs square planar, because this would actually be in the plane. And all of these are exactly 90 degrees. So the Y to the Y is 90 degrees, to the lone pair is 90 degrees. So this, going back up here, would be square planar. So we'll put X, Y, 5, Z as a square planar. And then the last one we have here is X, Y, 3, Z. Let's just come down here. X, Y, 3, Z. And so 3 plus 1, that's 4 groups. The electron geometry then would be tetrahedron or tetrahedral. And this group here would be, they're all equal positions, so you can put your lone pair wherever. They're all technically 109.5 degrees from each other. So this is going to be less than 109.5 degrees because we have a lone pair. And if you look at this, the structure here is ammonia, NH3. And this is going to be the molecular geometry with a lone pair is trigonal pyramidal because it makes a pyramid. So we're going to go back up here, and this will be trigonal pyramidal. So this one here, X, Y, 3, Z, is trigonal pyramidal. This problem is 10-3. Predict the approximate molecular geometry around each carbon atom of acetonitrile. Once again, on the exam, for something like this, you would be given the connectivity, because that would be hard for you at this point, I would think. But once again, carbon forms carbon bonds to each other. Okay, so it's asking to predict the molecular geometry, and that is what we've been doing. Okay, so the molecular geometry, we've been doing this. Once again, I'm going to refer you to table 10.1. You're going to have to be able to apply that without actually looking at the table. You will be not given that table. So try to understand a way to apply that table. So you want to check your work on page 434. So predict the approximate molecular geometry around each carbon, because your carbon atoms are the central. So the first thing you have to do always is draw a correct Lewis structure. So the first thing you do is the connectivity. So we have the connectivity, like I said, something like this where it's not straightforward. I think the connectivity will be given to you. And then you add your total valence electrons. So we have 3 hydrogens. They each have 1. So 3 times 1 is 3. We have 2 carbons. So 2 times 4 is 8. And we have 1 nitrogen. And nitrogen is in the 5th group. So that's 5. It's a neutral molecule. So that would be a total valence electron count of 16 valence electrons. Now we put them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, because we work our way. And now we check to make sure hydrogen has a duet. Those are happy. Nitrogen has an octet. Nitrogen's happy. This carbon has an octet. It's happy. This carbon is very unhappy because it only has 4 electrons. It does not have an octet. So if you remember, I told you the way to fix this is you take this lone pair that's closest and you make it into a double bond. So here we make this a double bond and we redraw the structure. And we put in our lone pairs now. We have just the lone pairs here and here. And then we check our octet and duets. So we got the duets, we got that octet. Nitrogen is good, 1, 2, 3, 4, 5, 6, 7, 8. But this nitrogen only has 6. Still unhappy. So we're going to do the same thing again. We're going to take this lone pair, we're going to put it here, and we're going to redraw it and make a triple bond. So we have a triple bond now. And then we have the lone pair here. Okay, so at this point we have drawn a correct Lewis structure. And it wants to know the molecular geometry around each carbon. So this carbon, the first carbon, going from left to right, is bonded to 4 groups. It has 0 lone pairs. So its molecular geometry will equal its electron geometry. And what would that be? that would be tetrahedral. So, and that's 109.5 degrees. So each one of these is 109.5 degrees. Now, the second carbon has two groups. See why I call them groups now? Two groups. It has 0 lone pairs. So once again, the molecular geometry will equal the electron geometry, and that would be linear. And that is the answer to that problem. This is problem 10-4. For the following structure, predict the hybridization about the central atom. Use superscripts as needed. Alright. Well, one of the things you might want to look at and start to kind of either memorize, when I say memorize, find some way to apply it, table 10.3 on page 456. Okay, that has the hybridization structures. Okay, so the way to work this is the hybridization. Basically, you have energy here. And in order to form these bonds, this compound had to use 6 orbitals. And six bonding orbitals. So there's 6 bonding orbitals used. And if you use 6 bonding orbitals, that's an expanded octet. So the example that your book gives you is on page 455. And they give you this sulfur F6 compound. So it would be kind of like that. So if you look for like a sulfur F6 compound, you would see that it has a 3s orbital, and then it has 3p orbital, and then it has available to it, whether it uses it or not, has a 3d. And then when these hybridize, they become a new orbital. They're no longer the p shape, the s shape like that. They're no longer the p shape like this, okay, or the d shaped, which I don't know really how to draw off the top of my head, so I won't. But we're going to use 6 of these orbitals. So here's 1, there's 3. See, 1, 2, 3, 4, 5, 6. We're going to combine all these and we're going to mix them all together. And we mix them all together, they come up with a new shape. Do I know what that shape is? I don't know. It probably has a little bit of this, and then it looks like this, and it might just be wobbly. Who knows? But they have a new shape. They're hybridized shaped. And you know how many there are? There's 6 of them. So I'm just doing these hypothetical shapes. Okay? I do know, like, if an S and a P orbital hybridize, then you get a wiffle ball. Instead of a dumbbell or an S, you get like a wiffle ball bat shaped looking thing. Okay, so they actually make new, and they're going to make 6 of them, and this energy here, they're going to kind of be hybridized in energy. So you're going to have 1, 2, 3, 4, 5, 6. And each one of these is going to be 1s, superscript 3, because there's 3 p's, and then there's 2 d's. And so there's 6 of these times 6. Each one of these would be called sp3d2, sp3d2, sp3d2. And then on the same energy level, you have 3d. These are unhybridized. Okay? Now, so that's their hybridization right there, sp3d2. And I think Pauline in her lecture gives you kind of a neat way to do this where you can count them. 1 S, a P, because there's 3 things, right? 3 P's, and then 2 D's. And so they should total up, these subscripts should total up to 6 because you have 6 bonds. So 3, 4, 5, 6, and they do total up to 6. That's kind of a nice way to check yourself and keeps you from having to totally memorize table 10.3. 10.5. Draw the Lewis structure of this arsenic compound, oxygenate type compound, and show all lone pairs. Okay, so now this is a Lewis structure you should be able to draw, right? Because there's just 2 elements there, and oxygen is going to be the terminal, and there's 4 of them. Now notice that you have a 3 minus charge, so when you do your total valence electrons, arsenic is in group 5, so that's 5 electrons. Oxygen is group 6, and there's 4 of them, so that's 24. And then we have a 3 minus charge, so we want to add 3. So this totals up to be 32 valence electrons. So now we add them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And if you do the formal charge for oxygen, they're all bonded equally the same. So you're going to have 6 minus your non-bonding. So you have 1, 2, 3, 4, 5, 6 non-bonding electrons plus you have 2 divided by 2 of bonding electrons, and that gives a formal charge of a -1. So each one of these oxygens are going to get a -1 formal charge. And then your formal charge for arsenic is going to be 5 minus 0 non-bonding plus 1, 2, 3, 4, 5, 6, 7, 8 divided by 2, which works out to be 4. 5 minus 4 is a +1, and that's going to be a +1. If you total that all together, it does equal a -3. So that's your correct Lewis structure. What is the hybridization of the central arsenic atom? Well, how many groups you got? You got 1, 2, 3, 4. 4 groups. 4 groups. And so the hybridization is going to be sp3. Right? So the superscripts there equal 4. So it takes 1 s and 3 p's. Okay? This is it polar or nonpolar? Well, it has symmetry. So what's going to happen is each one of these oxygen is going to pool. So keep in mind, now it would be polar if you had something different other than oxygen. So if you had a bromine or something different other than oxygen, but you have the same terminal element, you have symmetry. You have no lone pairs on arsenic. So that's going to be an overall dipole of 0, and that makes it nonpolar. Define the molecular geometry. The molecular geometry, you have 4 groups, and that's tetrahedral electron geometry, and it also equals molecular geometry because there's no lone pairs. So it's tetrahedral, and tetrahedral has 109.5 degree bond angles, and you just memorize that. Okay. Going on to the next problem. This is problem 10-6. Draw the Lewis structure for xenon tetrachloride and show all lone pairs. Okay, xenon's your central atom, and you put chlorine around each central atom, and it's a neutral molecule. So when we total up the total valence electrons, you have xenon is 8 plus you have 4 chlorines times 7, the group 7, so that's 28. So 28 plus 8 is a total of 36 valence electrons. So let's add these in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Sometimes I put a little electron cloud around here. Okay, is that okay? Yes, xenon is greater than n equals 3, so it can do an expanded octet. We learned that from last chapter. What is the hybridization of the central xenon atom? Well, we have 4 chlorines and 2 lone pairs, so we have 6 groups. Is that right? 4, 5, 6. Yes, that's 6. So you can do it like Pauline does. S, P, 3, D. So 1, 2, 3, 4, 2. sp3d2. So the superscripts add up. A 1 for S, 3 for P, and 2 for D equals 6. Okay? Now is it polar or nonpolar? Well, you got lone pairs, but you're going to have to look at its molecular geometry. So let's look at table 10.1. Let's look at what is the electron geometry, octahedral for 6. So remember in octahedral we put the lone pairs in the axial position, and then you would end up putting chlorine, I'm not going to put all the terminal ones here, in this planar, the square planar. So in that case, because you have symmetry, this would pull equally in all directions, and so this would definitely be nonpolar. So the answer is nonpolar. The molecular moment would be 0 dipole. So you got to look at its, when you're looking at polarity, you got to look at its molecular geometry. And you do that by table 10.1. Identify the molecular geometry. Okay, well, we just did that, right? That is square, planar, and its bond angles would be 90 degrees. Exactly. The next problem is 10-7. How would you know this? I don't think you'd have to be able to look this up from the standpoint to put in the lone pairs. I don't think that you would know this right off the bat, but I'm going to tell you. I call them happy elements in bonding. And so hydrogen likes 1 bond, 0 lone pairs. Nitrogen likes, if you're going to take organic chemistry, you might as well memorize this. Nitrogen likes 3 bonds, 1 lone pair. And this means formal charge of 0. Okay? So for these elements to have a formal charge of 0, this is what you look for. Carbon, 4 bonds, 0 lone pair for a formal charge of 0. Chlorine is going to have 1 bond and 3 lone pairs. And because you know that, you can put them in. So let's count. Carbon here has 3 hydrogens and 1 bond. See? So it has 4. 3, 4. So that one's fine. This carbon here has 2 hydrogens plus 2. It's fine. It has 4 bonds and 0 lone pair. This nitrogen here has 1, 2, 3. It needs a lone pair. Okay? Then you come here. Now, you might not know that, but that's a carbon. Okay, that carbon has 1, 2, 3, 4 bonds, so it's fine. This nitrogen, let's go to 2, has 1, 2, 3 bonds. 3 bonds, not groups, I'm talking about bonds. So it needs a lone pair because it likes 3 bonds and a lone pair. Okay, go to the next carbon. It has 1, 2, 3, 4. That point is actually a carbon. Okay, this nitrogen here has 1, 2, 3. It needs a lone pair. This carbon, number 3, 1, 2, 3, 4. No lone pair. The chlorine likes 1 single bond and 3 lone pairs. This nitrogen, 1, 2, 3, needs a lone pair. This nitrogen, 1, 2, 3, needs a lone pair. This carbon has 1, 2, 3, 4. It's fine. This carbon here has 4. This carbon here has 3 hydrogens and bonded to the carbon. It's fine. This carbon here has 1, 2, 3, 4. Carbon number 5. So it's fine. Nitrogen has 1, 2, 3, and needs a lone pair. Okay, now, after you do that, and you put in the lone pairs, now you can figure out the hybridization. So, of each one. So let's look at number 1. Number 1 is nitrogen, and nitrogen is connected to how many groups? 1, 2, 3, 4. So you got 4 groups. So you can just do sp3. See how the superscripts add up to 4? Okay, number 2. Nitrogen has how many groups? 1, 2, 3. See, 1, 2, 3. So 1, 2, 3 would be sp2. So the 2 plus the 1 equals to 3. So it's sp2 hybridization. This is problem 10-8. Diazine into H2, also known as diamine, is commonly used as a reagent for organic synthesis. Label each picture with the type of bond in diazine that is described. You can look and study the figures on page 449, 451, and 453 in order to work this problem. The shape of these molecules, this is a sideways overlap for the first type of bonding, and it's above and below the nucleus, and this would be a pi bond. Pi bond uses 2 unhybridized p orbitals. So the unhybridized p orbitals have the p-shaped orbitals that we talked about the last chapter. And so this is a p bond, which is a pi bond. And the next bond is a single bond. Pi bonds are also the double bonds. This is a sigma bond. And these shaped orbitals are, as you can see, if you can imagine, this is like the nucleus, and there's 1, 2, 3. 1, 2, 3. So if there are 3 groups, it's an sp2. Look at the superscripts, 2 plus 1, and an sp2. So this is a sigma bond. And that's kind of what they're looking for, but I'm kind of showing you a little bit more with the hybridization, sp2 and sp2. What type of bond is this? Well, it looks like kind of what you would see when you have a hydrogen 1s orbital with the little brown circle. And then once again, this would be an sp2. And this is a sigma bond. Okay, another topic you are required to understand is molecular orbital theory, and this is the last lecture of this whole course. This is section 10 or this is problem 10-9. You need to look at example 10-9 in your book. It's on page 462. And this is the last section in your book, 10.8. And this is molecular orbital theory, page 458. So you wanted to construct the molecular orbital diagram for H2-. The first thing you do when you're constructing a molecular orbital diagram, and remember, diagrams show where the electrons are. We talked about the electron configuration versus electron orbital diagram. You show your electrons with reverse spins because of Hund's rule, and there's two orbitals, or for every orbital you have two electrons in that orbital, and each orbital is represented by one of these boxes. And they usually ask you to calculate bond order, so I'll just go over that as well. Calculate bond order. Bond order is on page 461. Okay, so the first thing you want to do is you want to count how many electrons you're dealing with, how many valence electrons, because you're going to put the electrons in the molecular orbital diagrams. So in this particular H2-, hydrogen has one electron, one valence electron, and there's two of them, so that's two valence electrons. And then you look at the charge, and it's a -1, so you're going to have to add one valence electron. So you're dealing with 3 valence electrons. And when you put them in here, this hydrogen has 1 electron, and this hydride, it's called a hydride, would have 2. And that's how you get the 3. So you put them right in here. And these electrons have a certain energy. Now, the theory is when you have the molecular orbital, when the bond is formed, you feel the energy levels change. So you have bonding. So this would be a bonding orbital. And it is a 1s bonding orbital, so it would look like this. Those circles, and that would be what it would look like, and this would be the H and the other H. Okay? Minus. And that's how you get a sigma bond. That would be a sigma bond. So you just put 2 of them in there, and you're going to fill them up here. This is your molecule. These are your atoms. You see atom? These are your molecules. So 1, 2, and then 3. Now this star is an anti-bonding orbital. Anti-bonding orbitals, when you think of waves, so a bonding orbital is a constructive wave. So when these 2 electrons, which I think Pauline talked about, these electrons have wave functions. And we've talked about that in the other chapter. But this is constructive, right? So when 2 constructive waves come together, you can even have bigger waves. And that's a positive energy type. Now, when you have an anti-bonding wave, you basically have destructive. Okay, so this is higher in energy and is not preferred. Okay, so that's basically what the question's asking. Well, I'm going to go ahead and calculate bond order for you. I do BO equals the number of electrons in the bonding molecular orbital minus your number of electrons in your anti-bonding molecular orbital. So this is your star, and then you divide by 2. And the theory is the higher positive your BO number, your bond order, the more stable the compound, the more likely that is going to actually happen. So here we just count electrons. So we have our bonding orbital here. So we put 2, so BO equals 2 minus, and then our anti-bonding orbital here, 1, and then we divide that by 2. So 2 minus 1 divided by 2 is a positive 1/2. So that implies, because it is positive, that it would actually could be stable and the higher the positive value, the greater the stability. This is your last recitation problem for this course. So let's look at this. This is molecular orbital diagrams. Once again, this is section 10.8. Once again, the star indicates, you see the star? The star indicates the anti-bonding orbital. And that would be higher energy. And this is the picture of the energy levels for these different bonding orbitals. And so how do you do this? The first thing you do is you count your valence electrons. So here we have F2. There's no charge, so it's a neutral molecule. So fluorine is in group 7, and there's 2. So 7 times 2 is 14 electrons. And then what you'll notice is the order from left to right for these different orbitals show you from the lower energy to the higher energies. So you just fill them in from the lower energy to the higher energy. So we're just going to fill these orbitals in. 1 electron, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? So we got 14 electrons. And now we do bond order. And I will do that down here. Remember, bond order is the number of bonding electrons in your molecular orbitals minus the number of anti-bonding. And I'll just put a star there, all over 2. So for F2, we'll put BO F2. The number of bonding molecular orbitals, you just count the electrons that are in the orbitals without the star. So 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 minus the ones with the star. 1, 2, 3, 4, 5, 6. Minus 6 divided by 2. So 8 minus 6 divided by 2 would be 1. So your bond order is 1. Now, whether it's paramagnetic or diamagnetic determines whether it's attracted to a magnetic field. So if it's diamagnetic, and this is on page 467 in your book, it means it's not attracted to a magnetic field. And if it's paramagnetic, it would be attracted to a magnetic field. Now, if it's diamagnetic, that means all electrons are paired. Okay, if it's paramagnetic, that means there are electrons not paired. So what would this one be? Well, all the electrons in every orbital is paired. So this would be diamagnetic, F2. And that would mean that fluorine is diatomic in nature, and it is not magnetic. It's not attracted to a magnetic field, such as like iron. You know, iron nails are attracted to a magnet. That would be an example of a paramagnetic species. And if you do the electron configuration and the electron orbital diagram for iron, you'll see that it has like 4 unpaired electrons, which makes it highly magnetic. Okay, let's go to the next one. The next problem, you got a cation here, F2 plus. So basically you do the same thing. Your total valence electrons for 2 fluorines is 14, but then you got to account for this cation. So you're going to, when you have a cation, you're going to subtract, you're going to take away an electron. So you're looking at 13 valence electrons. Now you put the electrons in, starting from the lower energy levels to the higher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? Now the bond order for this compound, BOF2 plus. You count how many bonding molecular orbitals there are. 1, 2, 3, 4, 5, 6, 7, 8. Once again, those are the orbitals without the stars. And then you're going to subtract the anti-bonding. They have the stars. 1, 2, 3, 4, 5. Minus 5. Divide by 2, which is 3 over 2, which equals 1.5. So actually, so 1.5, okay. Interesting. Okay, is that right? Let's check that again. 1, 2, 3, 4, 5, 6, 7, 8. And we have 1, 2, 3, 4, 5. Okay. And so the bond over here is 1.5. And because you have an unpaired electron, this would be paramagnetic. And that would mean it would be attracted to a magnetic field. Now, I think that completes all these problems. Keep in mind, you will not be required to memorize this molecular orbital diagram. Sometimes they actually make you do that in general chemistry, but this energy level from the lowest to highest would be given to you, so that's nice. All right, well, good luck to you.